Now, if we have switches, we can do a bit more. So the last subsection was about physical infrastructure elements, real switches and cables, etc. But not always does the logical structure of a department, the working groups, for example, or the purpose of the nodes connected to a network fit to the physical structure. And this is a motivation for having virtual local area networks. So classically, we have the computer of an enterprise on a single local area network. Today, we have several of them. And I gave you several reasons why we have to separate them. So we have new cabling, we have new Ethernet technology, different departments have different local area networks because we want to separate them. It's maybe for security reasons, for load balancing. Remember broadcast storms and all this stuff. So maybe we want to separate it somehow. Maybe we want to say certain type of devices should go into one local area network, like the printers, because they do all this broadcast storming. I don't like this. So keep the broadcast out of other local area networks. But what happens now if you migrate with your computer? You belonged to one department, but now due to restrictions in office space, you have to work now here. Suddenly you're in another local area network, another physical local area network. So here we have maybe LAN 1, LAN 2, the physical structure. You cannot change it. You cannot rewire. And you all worked here, that's nice, but now suddenly you have to move because there's not enough space in the office. But you still want to feel like being part of L1, although you're now sitting in L2 in the network. And the idea here is we create virtual local area networks. So we configure the LANs logically, not physically. So we decouple the logical topology from the physical topology. And that's the basic idea of VLANs. So in a VLAN, you can collect, for example, all the printers. Or this is the student network and we separate them from the professor's network or from whatever, the administrative network, or from whatever you like to separate. Physically, we all belong to the same network. Think of wireless LAN. We're all in the same wireless LAN. Or think of other local area networks. We plug our computers in and then we are connected to this local area network. But logically, we belong to another group. To do so, we need VLAN-aware switches. Yeah, all the larger switches can do this. And then we can create different VLANs, virtual local area networks, and we quite often name them by colors. So this is the orange network and the gray network, for example. And this helps us to draw diagrams showing at the same time. So here, this is the group of the orange users belonging to the logical orange network here. And then we have the gray ones. But you see, there are some orange users, they are attached to this local area network 2, created by the switch number 2, and some of the orange are attached to the local area 1, created by the switch number 1. So you see, the physical topology does not match the logical topology. Okay, so our VLAN-aware devices, they now know how to handle this issue. So the switch has a table that tells which VLAN is accessible, for example, via which port. So that is the idea. So why not doing so? And then those devices in between, they know if I have to forward packets, a certain port only forwards orange packets and never the gray packets. So if the gray network in our case misbehaves, then this hurts only gray nodes, not orange ones. So even if you have a broadcast storm in the logical gray network, the broadcast will not go over into the orange network. So there's no way on this layer 2 to communicate from one VLAN directly into the other VLAN. So they are separated. And this is why quite good when it comes to security. You cannot really do this if you have these simple systems as shown on the left-hand side, where you then forward into segments of this classical Ethernet, whatever, gray and orange packets. So this is why we rather have the system like on the right-hand side, where you have the switches, and the switches can really isolate traffic. So there's no way of then receiving orange packets if you're node D. That means also if you sniff for whatever packets, you simply will not get them. So the switches will separate. The question is, how does a switch know anything about the wireless LANs? So we need those VLAN-aware switches, and there are different solutions. So for example, we could say, okay, if we have a switch, we can tell the switch, so this is for example orange, this is also for orange, and this is for our gray network. So we assign ports to certain networks. So that is the idea there. And then if you connect a device here, then you automatically belong to the gray network. So if you move from one department into another one, the system administrators have to reprogram the switch and tell the switch, now this port, although you sit in the middle of the orange department, this port belongs to the gray department. That's one of the solutions. There's another solution. We can use the MAC addresses. So we can basically say, okay, this MAC address now belongs to a certain VLAN. So that means your device has a certain 48-bit MAC address, and you assign the MAC address to a VLAN. So you have a list of orange MAC addresses and a list of gray MAC addresses. And so no matter where you connect your machine, the switches know if a packet arrives with this MAC address, this belongs to orange. And even if the destination belongs to a gray MAC address, the switch will not forward it, because it will only forward from orange to orange. So that is one way of doing so. So that means if orange wants to send something to gray, the switches will not do it. This is why you need a router. Then you have to use a router, and the router will then interconnect gray and orange, but not on layer 2. And the routers will filter out broadcasts and all this stuff. There's a third solution as an example, that for example, that we use high layer addresses protocols and say, okay, IP traffic is now in a VLAN, or if we see that this is audio video traffic, this is a VLAN. This violates the layering idea, but this also can be done depending on your system. There's a standard for this, 802.1q, and this specifies the fields in frame header telling, okay, where does it belong to? Wait, we redefine now the frame header. So what happens if your Ethernet card cannot handle this legacy Ethernet cards, and who generates then this, and what happens with the maximum frame length? The solution is as follows, that as soon as there's a VLAN-aware device, this could be the switch, for example, the switch adds this VLAN tag and also removes it. So if you connect a non-VLAN-aware computer to a VLAN-aware switch, the switch can insert this tag. All the new network interface cards, they support this. So, and we can even have nested VLAN tags if we bridge VLAN over other providers, so VLANs of VLANs and stuff like this. So how does it look like? So the frame format now says, okay, we use a certain identifier here that tells us, oh, this is now not the classical length type field. So we have a protocol identifier. We learned that if in our length type field there's something larger or equal to 1536, this means it's a type and not the length. So we use a special type, and this then tells us, okay, this is now a special frame, a VLAN, and not a classical one. Then we have certain other fields, TCI, and this now contains a priority field. This has nothing to do with the VLAN. That's also a drop eligible indicator, has nothing to do with the VLAN. So if you update a standard, you also pack in some more things. So this has nothing to do with the VLAN. And then finally, we have the VLAN identifier. That's the only interesting thing here in the context of VLANs. This is our 12-bit identifier that gives us, in the end, because we have some reserved numbers, 4094, which is quite a lot, possible VLANs. So this is the one we need. The TPID, we only need to tell the system, oh, this is now a VLAN Ethernet packet, and then we need the identifier. So this is our 12-bit identifier for VLAN. That's the basic idea. So this helps the switches to distinguish between the orange and the gray and the red and the blue and the whatever network. So typically you have something like 5, 6, 7 VLANs in a department, and then you can distinguish between maybe audio video traffic from other traffic, and you can do a bit more if you use those priority code points. Then you have different classes of service, but this has nothing to do with VLANs. This is then how to prioritize different traffic streams. We'll come back to this when we discuss on layer 3 what we can do more than just, well, stupid datagram unacknowledged best effort traffic. Okay, virtual LANs, that's a logical infrastructure on top of the physical infrastructure. So the final subsection, OTNs, optical transport networks. We are here, well, presenting some infrastructure, so some physical elements, how you do it in the small virtual LANs, real LANs, spanning tree, etc., but also in the large. So how do we transport data over long distances, masses of data? There were many, many different standards for this. Older standards, there were ATM systems, SDH systems, SONET systems, etc. But they all had their limitations. They come from the classical telecommunication industry, hierarchies of time division, multiplexed voice streams. They had certain upper limits, 40 gigabit per second. We want to go faster. We already learned with Ethernet we can go faster. But there are already many different technologies. So storage area networks, fiber channel technology, connecting compute centers, storage components. There's the Ethernet technology. There's the classical SDH, SONET from the telcos technologies. There are some other video standards, etc. So there are many different technologies out there. And we cannot simply say, okay, let's get rid of SDH completely and all the traffic. So there are some special requirements. So ITU-T came up with a family of standards, G.709 and some others, developing an optical transport network that really scales to several hundred gigabit per second, offering forward error correction and different frame rates, that is able to transport classical, historical, legacy systems, SDH, SONET, different Ethernet speeds, 10, 40, 50, 100 gigabit, but also directly IP packets, all these things, and supporting constant data rates, but also variable data rates with many, many really fancy multiplexing versions. So yes, this makes it more complex, but the basic idea is today we are that extremely fast. We have so high data rates. We can waste a bit into wrapping the other data, and that's the core idea here. We want to transport, for example, our Ethernet packets in a transparent way, Ethernet or whatever we have. So we insert a header with a lot of forward error correction. We multiplex many data streams, and we place this forward error correction somewhere. So we create a wrapper. And because we are that extremely fast, high data rates can go up to several hundred gigabit per second, we can easily wrap lower data rates. Yeah, we'll waste a bit, but as we multiplex all the traffic over fiber, dense wavelength division multiplexing, DWDM, oh, well, we can spend a bit for the header. So how does it look like? I will not go into all the details, just to give you a first idea about this technology. So core goal is we want to lower the cost per bit. We want to simplify the technology. So we want to use a common transport technology. We want to have less equipment. We don't want to have a special equipment for Ethernet, another one for SDH, another one with ATM support. But we still want to have features like point-to-point connection, or a ring with some resilience, or a meshed network. We want to be able to isolate faults, to improve troubleshooting. So what is the key idea? So shown here is we take directly from the standard, we take the client data here, and then first of all we place the client data in something that's called the optical payload unit. And there we have a header for it, as we know it from all this layering, but this is all down. Basically this is all layer 2 and lower. So we place it there, then we can place this, several of them together there into other packets, multiplexing many of the data streams, as we'll see in a second. So we multiplex many of them, and so on. We go down all the layers until we create a frame that is able to be transported with the help of optical signals. There are even some more layers there, but that's the idea. So you wrap something that you wrap, that you wrap, that you wrap, and multiplex a lot, but in a way that you are flexible. You remember the hierarchies we had for these voice channels, for example, where we had this very strict time division multiplexing. That's technology from the 60s, 70s, 80s. Today, we have more powerful systems, and there we can do it in a way more flexible manner. So we start with this optical payload unit, and that's the structure that adapts to the client information for the transport over this OTN system. So it has all the client information with the overhead. We do rate adaptation because we may have a different rate between the client and Ethernet or whatever, and then the payload in this optical system. And so we have some signaling overhead. And then we do all this multiplexing together. We create optical data units and optical transport units. So for you, it's not that important, all these names, just to give you a first impression how this is done. And the idea, yes, this looks a bit complicated in the beginning, but it is as shown here on the right-hand side. We take one of these data units, optical data units, and inside we have, for example, STM16, that's a signal from this classical, very strict multiplexing, ATM also, legacy technology. We have generic framing protocol, so this could be an Ethernet frame, for example. We insert a lot of redundancy, some alignment because different data rates, and then we multiplex, for example, 4 times such a frame into the next level of hierarchy, and then we take this and add some more forward error correction, some more redundancy to be able to reconstruct the original data if there was an error. So this is the rough structure where you basically have your original data, optical data unit, and you insert some overheads depending on where you are on this layer. So, example, 100 gigabit Ethernet goes into a certain ODU4 in this case, offering 104 point whatever gigabit per second. You see a bit more because we have some signaling, so some rate adaptation. Then this ODU4 then can be transported via this OTU4 with again a bit higher required data rate. Why? Because we have some recovery mechanisms for FEC data. And then this OTU4 can transport this 100 gigabit Ethernet stream, but it could also transport 80 ODU1s with 1.2 gigabit per second, or 10 ODU2s, and so on, and so on, and so on. So you see, a very flexible format. And we can be flexible because today we can spend some 100 extra bits for this FEC, for alignment, for wrapping, etc., because we have these extreme high data rates. Remember, in the lab, already more than petabit per second for a fiber. So this is very flexible, and please go ahead, look into the standard, and this shows you many of these options just to give you a first impression what you can do. This is when you look in the standard and you say, okay, where do I find my data? Well, in the end, your data is somewhere in here, but you'll find many more additional fields that are important, for example, for path monitoring. What's going on my path is if something happens. There are many bit fields in here to do error checking, for status, for payload type identification, for measurements of delays, and so on and so on. So if you have to work with it, then you have to look into the standards, so no one learns this. This is just an example with many detailed definitions from how we adapt to different client signals. And that's the key idea of OTN, that we are able to transport basically everything. And then we use a common system. That means common devices, common interfaces, but we're able to transport all of this. And then over time, we can say, okay, goodbye to certain technologies, then we don't use these wrappers anymore, but we still stay with OTN. So, summary of the link layer. So we saw physical layer is really this bit-by-bit transmission from A to B, different physical media, wire, fiber, radio. And now our link layer enables the transmission of flows, of coherent, error-controlled structures of bits or frames from A to B, if A and B are directly connected. So that was the very first simple case. And we can go there from 100 megabit per second to several hundred gigabits per second. Okay, in the Ethernet case, in the wireless case, already 2 gigabits per second, but there are some restrictions here. Also, classical legacy systems can go up to hundreds of terabit per second, now transported via OTN. So we did some first refinement to this basic idea, A and B directly connected. So there might be several receivers, then we need some multiple access. Okay, that was the first refinement. And the second refinement was, okay, maybe we want to bridge longer distances, more complex networks. This is where we need some relaying services on different layers, switches, hubs, bridges, repeaters, etc. We had a closer look into Ethernet. We learned that, we can use this on local metropolitan wide area networks, Wi-Fi, and of course mobile communication. We also learned that this relaying using switches, for example, does not really scale. So this is where we need something else. And for global scale, we need different framework that is more efficient for different link layers. And this is then where we go to the higher layer. So to make it more scalable, we need a different addressing scheme, and we need some mechanisms to really build end-to-end paths. Because remember, layer 2 is only valid between one NIC and the next NIC. This is where layer 2 exists. And then there's the device. So layer 2 goes from your computer to the switch, and that's it. So there's no layer 2 going across the switch, across the router to some other device. So we need more mechanisms. And this is exactly why we have a layer 3. We need a network layer that provides for this functionalities, bringing together different link layer technologies, scalability of addressing, building up end-to-end paths. This is where we have layer 3. So looking back, what are the reasons for virtual LANs? We saw we have physical local area networks, but we also have virtual ones. Why? What do we do with the virtual ones? And if we have switches there in between, we need them. How do we find out where does this frame belong to the orange or to the gray? We can even nest VLAN tags, so why doing so? This has something to do with the providers, etc. Then I briefly introduced the idea of OTNs. What was the key motivation? So look up OTN and what is the motivation? Why going for OTN? Why stopping, for example, providing SDH SONET services? And why do we have so many layers? It looks really complicated, all this OTN stuff. Why do we have that many layers and parameters, etc.? To get a better understanding, well, it's a good idea just download the standard and just, you don't have to understand all the bits and all the details, but just to see how is a certain technology reflected in the standard and what can you wrap, how can you adapt this, then also you get a better feeling how standards like this look like. And they're different from the RFCs. We learned a bit about RFCs, IETF standards, and also different from IEEE standards. Here, this is a standard from ITU-T.